Hello, this is El-Sharif Mahmoud. In this video, I will be implementing jump register instruction. Jump register instruction basically changes PC or the program counter to the address assigned or the address stored in this register. So PC to register RS. So by looking at MIPS sheet, we can see that jump register is an R-type instruction, and it has the following format. This format where the opcode is 0 and the function field is 8 hexadecimal. Okay, so a question that comes in mind: how do we differentiate between jump register and any other R-type instruction that does not involve actually changing PC? Okay, so the answer to this question lies actually in the fact that the function field is unique for each R-type instruction. Although the opcode is the same, but the function field is unique for each R-type instruction. So a good way of differentiating between jump register and any other R-type instruction is to actually extend another line to the main control unit, so that it recognizes that this is not a normal R-type, it's just jump register type instruction. So by extending a new line here with instructions from so basically instructions, let's look at the format here. So from 5 to 0, so instructions from 5 to 0. That way we can actually know whether or not this is a jump register or any other R-type instruction. So to reiterate, we basically need to create an instruction that simply changes PC from PC plus 4, like from being PC plus 4 to being the address contained within RS. So this means like the selection involves a mux. So instead of actually adding a new mux, we could take advantage of the muxes that are already used within this data path. One register that we can use is actually jump. So we can extend this one multiplexer. So we can actually extend this to take the data from RS as an input and assign a control value of 2 to this input. That way we can actually select between the address in this register, the jump address, or the result of this multiplexer, of the branch multiplexer. One thing to note is that despite the fact that this is an R-type instruction, the ALU in this case is not used at all. So we don't really care about what instruction 20 to 16 contains, or the control variables that the control signals that control the ALU or the register destination. So now we will determine the control signal values. For register destination, since we're not actually writing to memory, we don't really care what the register destination would be. So basically it's X. What else? For jump, we need it to be, since we extended it, we need jump to have the value of 2. For branch, we don't really care since it is actually, this multiplexer is coming before the multiplexer of jump, so it's X as well. Mem read, we don't really read from memory, or we don't really care if we read or not, so it's X. Mem to reg, again, since we're not actually writing to memory, to register, we don't really care about this. ALU operation, since we're not doing an ALU operation, we also don't care. Mem write, we're not writing to memory, so it's also, okay, so here's the thing. Since we're not writing to memory, we have to actually assign it to 0. For ALU source, it's X, we don't care. For register write, we shouldn't write to any register, so it should be 0. So whenever you're changing, so whenever a control signal that involves changing the memory or register, we have to be careful in choosing the control signal. So in that case, we need to assign it to 0. So this is how you implement jump register. Thank you.